Hello and welcome back to a little further discussion of applying now what we know about sinusoids. The basic form that you've seen in your textbook or in Algebra 2 is given on the top here, and then some definitions. And remember now, we'll be working with a period and trying to find the horizontal dilation factor. So if we look at a problem like this where a weight's attached to a long spring, it's bouncing up and down, and as it bounces, its height above the floor varies sinusoidally with time. We could understand the situation to be that at 0.3 seconds, this weight sits at a height of 60 centimeters. So this would be a height, and this would be time. And later on, at 1.8 seconds, it's now at 40 centimeters. And give ourselves a bit of a frame of reference here. We draw some dashed lines. And at its height, 0.3, it's at 60, and then 1.5 seconds later, it gets back down to its minimum. Sketch a graph of the height of the weight above the floor as a function of time. Mark scales on your axes, and draw at least one full cycle of the weight's motion. Well, the basic shape is going to look something like this. We're going to double this length of 1.5 seconds. That gets us out to roughly, or exactly, 3.3 seconds. And at that time, the weight is back to its highest point, and it gets there sinusoidally, something like that. All right. What we really want is an equation to help us find future values. And when we look at this, we know that the middle point, the average height, is going to be 50. That's our sinusoidal axis. The amplitude is 10. That's how far above and below the sinusoidal axis our weight ends up. The dilation factor is a bit challenging. We're going to hold off on that, but we know that it starts at 0.3 seconds. So the only thing left to really look at here now is this horizontal dilation factor, and it equals 2 pi over the period, which in this case the period's 3 seconds. So we just put 2 pi over 3. All right. Now this is a useful equation. We're going to use this in the next slide. We want to know when time is 17.2 seconds. We get 43.31 roughly. So h of 17.2 equals 43.31 centimeters. What was the height of the weight when the stopwatch started? Well, that one's actually a bit easier, I think. We simply plug in a 0 here. So we'll go back to our 17.2. Now, it might be tempting to say it's 60, but we know it's not 60 because that's the value at 0.3. We get 58.1 roughly. So h of 0 is 51.1 seconds, or centimeters. And I think you understand how this works then. Now it's going to be a little more algebraic. Now we want to know when this height equals 59. So we're going to have to undo. This gets a little more challenging, but math we've done before. All right. So now we have the cosine of our stuff here equals 0.9, and we're going to undo cos with arc cos and get into all that fun stuff. So pull up our calculator, second cos of 0.9, we get 0.45. And we're going to go ahead and separate these right away. So we've got 2 pi over 3 t minus 0.3 equals 0.45. And the same stuff where we have a negative. Multiplying by the reciprocal, the whole equation, we get t minus 0.3 equals the 0.45 times 3 over 2 pi plus 2 pi n times 3 over 2 pi. Okay, now we're going to evaluate this thing using the calculator. And we're going to be careful about this because there's some dividing that I want to make sure comes through properly. So I'll divide by 2 and then divide by pi. And I get a 0.2 there. With things canceling out, I get a 3n. Of course, on this side, when I divide or multiply by the reciprocal, 3 over 2 pi times the whole equation, I end up with a similar problem. I get this 0.45, negative 0.45 times this business. So I'll just get the same value, just with the negative sign in front of it. And so I get t minus 0.3 equals negative 0.2 plus 3n. And to finally solve for t here, adding the 0.3 to both sides, I get two starting values here, a 0.1 and a 0.5, and I wanted the first positive value. So my first positive value is going to be the t equals 0.1 seconds. On vacation in Maine, you notice a seawall that has markings to show the depth of the water in the ocean at 7 a.m., 7 hours past midnight. Water is at its low tide, which is a height of 10 meters. We'll put a 10 there. And at 1 p.m. you see the water reach its highest point of 24. So out here at, I'm going to call it 1300 so that I can keep track of the hours a little easier. And what we have is some kind of a tide measurement that does not go below 10 or above 24. And the total time here for lowest to highest looks like it's 6 hours. So if we go another 6 hours here, we're up here at 19. And our low tide point to high tide back down. Something like this. All right. I'm going to come up with an equation for this then. We've sketched the graph. And I'm going to write the equation here. To find the sinusoidal axis, you can just get the average 10 plus 24 divided by 2. So that's 34. Half of that is 17. And you go up and down 7 for the amplitude. The starting point for the cosine curve is at its peak, its highest point, and that's at 13 seconds, or sorry, 1300 hours. And now we try to find our horizontal dilation factor. We know the period is a total of 12 hours, so B is going to equal 2 pi divided by 12, which is pi over 6. All right, and this is going to be a useful equation. Use the equation to find the depth of the ocean at 3 p.m. Well, 3 p.m. is going to be 12 plus 3, 1500 hours. So H of 15. I'm going to go to our calculator. We get 20.5 meters. This time we want to find out the time after noon when the depth of the ocean was exactly 15. So we're going to set our equation equal to 15 and undo some operations. And of course, we're going to undo cosine here with our cos, giving us this equation, plus and minus the inverse cos of negative 2/7 plus 2 pi n. And that value we need from a calculator. .86. All right. And that should make some sense. That's the first quadrant for cosine's principal branch. That's negative. It's past pi over 2. Pi over 2 would be about 1.5, so we're over it a little bit further at 1.86. Now we're going to undo some more operations here. Multiply this whole equation here by the reciprocal, 6 over pi. So we'll get a plus 12n now there. This calculation. .56 we'll call it. All right, last step to undo the plus 13. And remember, this plus and minus 3.56, you actually have to separate that because you're going to get some different values out of that. And we're not going to add this to our period here of 12n.